Welcome everyone to this statistical field theory and quantum phase transition. And this is the graduate level course given by me. And this is my name and my office phone number and my email. This is the textbook that we use in this course, Lectures on Phase Transitions, Renormalization Group, written by Nigel Goldenfield, who is a well-known theorist, theoretical physicist, Illinois, Champaign, United States, and this book is well written. My lecture notes are basically from there, okay? And you could borrow the book. You don't need to buy this, but this is good to have that. Good. So what is the main focus of this course? Well, as I mentioned, we like to study the phase transitions. So what is the simplest example of the phase transition? From your elementary school, you must learn the ice, when heated, will be melted into water, and if you heat up the water and this water will be evaporated. The ice and liquid water and the steam is kind of a classic phase transition that we all know from our childhood. However, there are many different kinds of phase transitions occurred in physics. And this is the main topic of this course. And we will study different examples of the phase transitions occurring in nature, especially in physics. And we would like to study how that occurred and why that occurs. We like to quantify such transitions by scaling laws and renormalization group analysis. So this is the purpose of this course. Let me just illustrate this point a little further by using this plot. Here, this is the phase diagram of a quantum mechanical system or even classical system as a function of temperature and some control parameter, which I call G. As you vary temperature and this tuning parameter G, there are different phases or ground states that could occur in this system. For example, for this parameter G, very, very small or close to zero, the system may become ordered, just like the ice molecule actually displayed in a periodic way on a cube, right? So that's the crystal structure or any other, say, magnetic ordered at low temperatures, certain range in parameter space. However, this ordered phase could actually become disordered as you heat it up, okay? For example, if you increase temperature of the system, and this ordered phase could become disordered. In the very simple example of this magnetic materials, for example, the spins of these atoms may become parallel to each other in a low temperature and small g regime, that all spins are ordered. But if you increase the temperature and the spins will become fluctuating and disordered, at some point these spins are oriented in any arbitrary directions. So in that case, it is actually a paramagnetic state where there's no preferred direction for the spins to orient it. There is a temperature which is this borderline here in the white curve that separates this ordered from the disordered spin system. This is precisely this transition, the phase transition that I just told you about. Ice get melted into water, so the ordered spins become disordered spins as you increase the temperature. Okay, so that's the example of the classical phase transition where the ground states of the system changes if you increase the temperature, okay? Or the state of matter as you change the temperature. So this thermal excitation induced transitions is called classical phase transition because that follows classical statistical mechanics. And this phase transition that we will be talking about will start from here, that we introduce some examples of a classical phase transitions like spins or liquid, gas transition and so on. However, for a quantum mechanical system, there's another transition called the quantum phase transition, which is the transition of a ground state of a quantum mechanical system from one phase to another phase. For example, if I call this ordered phase A, and another phase is again the disordered phase called B, and we can imagine that as you change your parameter G, and at some point these two phases are having almost the same free energy or ground state energy, and right at this point you see the system doesn't know where to go. For G slightly above GC, and the ground state of the system changes from state A to state B or from phase A to phase B, but this transition occurs at 0 temperature. In other words, the quantum phase transitions occurs at T equals 0. So that is the ground state phase transition. Unlike this ground state phase transition, this thermal excitation induced phase transition, which we call this classical phase transitions, occurred at a finite temperature, and that temperature we call this critical temperature. So this critical temperature Tc changes as a function of tuning parameter G. So as you tune the parameter G bigger and bigger, this Tc gets suppressed, gets decreased further and further until Tc vanishes right at this quantum critical point Gc. And in between phase A and phase B, at the finite temperature, we have a very interesting region which we call this quantum critical region, where many physical observables show non-trivial power law behavior. We will discuss later. Quantum critical region fascinates a lot of theorists and experimentalists in condensed matter physics. Okay, so that is another key point of this topic, but we may not have enough time to discuss important phenomena of this quantum critical region, but we have sufficient time to talk about this classical phase transition in this course. So, but at the end of the semester, I think we will be able to talk about this quantum phase transitions and quantum critical phenomena. It depends on how much time we spend on this classical phase transition. So this is just a very general description of what topic that we're talking about this course. So below, I will introduce the outline of this course, tell you specific topics and steps that we will discuss these transitions. First, we will talk about the scaling and dimensional analysis, and we will talk about power laws in statistical mechanics. The second part of this course is about the phase transitions in principle. So in the first part, we will introduce the phenomena of phase transition in a more mathematical way. Namely, we introduce the scaling laws and the power law behaviors of many observables when the system undergoes such classical phase transitions. And these power laws, scaling behaviors, are a typical hallmarks of this physics. And we will learn this kind of phenomenon in different examples. The second part is to ask the question how this can occur in principle under physics laws. So how the phase transitions occurred in principle. So why the phase transitions occur. Okay, so why do we expect that the phase transition occurred? So to that regard, we will first introduce different types of transitions. There are only two types of transitions. So number one is called the first order transitions. Number two is called the second order or continuous phase transitions. And we will introduce this finite size effect and this correlation length. The concept of correlation length is extremely important when talking about the phase transitions. It describes the length scale over which certain relations are obeyed for the system. Okay, so as the system approaches this critical temperature or this critical point, then this correlation length diverges. So that is another key point of this transition. This correlation length C diverges when we reach this phase transition or the critical point. And then we will talk about the role of models. We will introduce different model systems, or toy models, which allows us to analyze more easily these transitions. Okay, for example, in the spin systems, we will talk about the Ising model, and we will generalize this to XY model, and also the Heisenberg model. These are just names for now, but I will tell you more specifically what that means when we mention this different magnetic or spin models. And from these simple models, then we could derive or prove the existence of the phase transitions. And we could further introduce this spontaneous symmetry breaking. So the idea of the spontaneous symmetry breaking is the key to understand why this phase transition occur. Okay, so it has everything to do with this kind of symmetry breaking, okay, of the system. So we will talk about the spontaneous symmetry breaking and the arise of this phase transition and the link between these two. Okay, so we will talk about this relation between different systems. For example, fluids, the lattice gases, and the spin model, say Ising model. And we will talk about different physical realization of these phase transitions, different materials, and we will demonstrate that despite of these different systems, the spins and gas and the fluids, and at the transitions, at this critical point of the critical temperature, so they all behave the same. So it's called equivalence in statistical mechanics. And this kind of equivalence is called universality or universality class. So this is again a key word or key concept when we describe these phase transitions. So in other words, this is magic of this phase transitions. Namely, despite of the apparent different compositions among fluids and lattice gases and Ising models, or you can just illustrate or think about other examples in physics that very different systems, but they all have these phase transitions like this. And at the critical temperature, the critical point, all the physical quantities in all these different systems behave exactly the same. So what do I mean by exactly the same? Well, I will define that later. But experimentally, of course, you will detect this different system by different experimental techniques. But whatever the quantities that you measured, the systems, at the transition, the close to transition, their correlations or physical observables near the transitions for completely different systems, they all follow the same scaling behaviors or the power laws. So these is the key observations of all these phase transitions, that physical quantities obey power laws or scalings. And different materials or different systems, if they belong to the same universality class, and they should have the same scaling or power law dependence on your experimental tuning parameters. So we will come back to this when we discuss this universality class. Chapter 3 of our course is about phase transitions practice. Remember, previously we talked about how the phase transition occurs in principle. So we should study statistical mechanics again and think about how this phase transition occurs in principle based on the statistical principles. After that, we should ask the question, how this phase transition occurs in practice, namely in a particular model system, say the Ising model or the other models. So for example, we will talk about this Ising model in one dimension, and we will use transfer matrix, and we calculate the spatial correlations, and also we apply the mean field theory to really calculate observables that we could detect the phase transitions to occur. So that's chapter 3. We use a specific example in this towing model, and we do some calculations, and we find that indeed there's finite temperature phase transitions in that model. And chapter 4, we will study critical phenomena in fluid, again based on what we know about this fluid dynamics, this van der Waals equations, and we will calculate these critical exponents near the phase transition. So that's chapter 4. And chapter 5, we introduce the Landau theory. This theory is developed by Landau in the 1950s to describe phase transitions and critical phenomena by introducing a free energy called the Landau free energy. And we will introduce first the order parameters, and these order parameters, remember this phase diagram that we just plotted, and in the ordered phase we could describe this order by so-called order parameters. For example, the magnetization or spin moment of magnetic materials in the ordered phase shows non-zero magnetizations, and average be non-zero, and that is the order parameters. In the Landau theory, we can define order parameters to really identify this ordered phase. Further define this Landau free energy. It is a phenomenological free energy based on this order parameter. We could derive a mean field theory to get these solutions within the Landau free energy functional by minimizing the Landau's free energy functional with respect to the order parameter. And then this is called the mean field theory within the Landau's theory. And this phenomenological Landau theory actually can tell us whether the system shows the first order transition or a continuous transition. And again, so we will formally define what I mean by the first order transitions and the second order phase transitions later. And we can also calculate these critical exponents within this Landau theory. We could just generalize this to the coarse graining processes in homogeneous systems. So we will talk about this. Okay, we could calculate correlation functions at all. This is all within the Landau theory. So this theory is very successful in describing many different classical phase transitions driven by thermal fluctuations. However, Landau theory can actually break down when we consider some fluctuations. So that's the chapter 6. We should talk about the fluctuations and the breakdown of the Landau theory. By fluctuations, I mean mean field theory describes some uniform solutions of the ordered phase by assuming that these order parameters are simply just spatially homogeneous variables distributed over space. This is just part of the story. But if we simply refine this theory further by considering the fluctuations, spatial fluctuations at all different locations, and that fluctuations could actually cause this breakdown of the Landau theory. Therefore, we should describe the fluctuations within the Landau theory, and we will introduce called the Ginzburg criterion, which says that for a spatial dimension d greater than 4 or 3 plus 1, 3 spatial dimension and 1 time directions. So in this case, when d is larger than 4, the mean field theory is actually exact. The Landau's field theory is actually good, but for d is less than 4, say a low-dimensional system, then this fluctuation is going to kill the Landau's mean field theory. And we will talk about that. And we will introduce this Gaussian theory and critical exponents. The Gaussian theory is actually the approximation. Consider fluctuations above this Landau's mean field theory. And based on this Gaussian approximated theory, we can calculate critical exponents. And we should compare these critical exponents with the exponents that predicted by this Landau's mean field theory. We will also introduce so-called anomalous dimensions, which allows us to do this dimensional analysis of the Landau theory, and we will talk about that later. Okay, so there's anomalous dimensions involving here when we consider these fluctuations and the breakdown of the Landau theory. Again, we will discuss the scaling in static and dynamic phenomena. So based on these fluctuations beyond the Landau mean field theory, and we could just calculate the critical exponents and describe these power law behaviors of observables, calculate scaling laws and predictions based on this calculation. But we should emphasize that this scaling is a key concept when we approach this critical point, the critical temperature, and this concept is actually extremely powerful. But it relies on a hypothesis called the scaling hypothesis. Namely, we should actually assume that free energy or Landau's free energy density shows such scaling properties near the transitions. And this is our hypothesis, which we haven't proved until later we predict certain scaling laws and critical exponents and so on, and we could compare these predictions with experiments, and then we actually go back to this hypothesis and we say that this hypothesis actually works. But beforehand, we don't know whether the scaling hypothesis works, but we nevertheless propose that postulate that there's a scaling behaviors near the transition, and the scaling hypothesis allows us to write down the free energy as a function of the scaling laws. And we should write down the scaling hypothesis for free energy, and then we get all these predictions, critical exponents and correlation length, divergence, and so on and so forth. So this is a very important part of this analysis that allows us to use the scaling hypothesis for the Landau's free energy density functional to actually derive all these power law behaviors of the observables close to the transition and extract those critical exponents and all these divergent power laws that we care about, and is the heart of this chapter 6. So let me emphasize the scaling behaviors of the systems that are close to transitions, especially the classical phase transitions. Scaling refers to the power law relations. So near the transitions, as I mentioned earlier, for classical phase transitions, we have a Tc, which decreases as a function of increasing its tuning parameter g. And before Tc vanishes, there's a finite width around this Tc, we call the critical regime. And we can define this dimensionless quantity called little t, which is magnitude of difference between the temperature that you are probing and this Tc line right here, okay, and divided by Tc. So this quantity measures the distance to critical point or critical temperature. So the scaling laws or scaling relations tells us that many physical observables show a power law relations as a function of the little t, or applied field, a magnetic field, H. So for example, as we will see later, that many classical systems, when they reach to the critical temperature, for example, magnetization for a spin system, behaves as a power law in terms of this t to the power beta, where beta is some fractional number, which can be rational or irrational, and oftentimes those exponents are irrational number, called critical exponents, exactly at Tc, but if you apply the small field, magnetic field, for the spin system, and magnetization behaves as h to the power of 1 over delta, where delta is another critical exponents. You could also measure the specific heat of the system when it close to this phase transition, and this is called CV, or specific heat capacity, which is proportional to t to the power of minus alpha, which means that the specific heat diverges in a power law fashion with exponent alpha. And likewise, you could also measure the magnetic susceptibility or spin susceptibility of a spin system when it close to this order to disorder transition at finite temperature, and it behaves as a power law in a little t to the exponent minus gamma, and again gamma is another critical exponent. And we can also calculate this correlation length C, as I mentioned, earlier that this measure this distance over which all these critical behaviors, and this correlation length diverges in a power law fashion. So the critical exponent nu is called correlation length exponent, which tells us how divergent is the correlation length as the system approaches to Tc, both from above or from below. And again, we could also calculate and measure this correlation function g as a function distance, which measures again this relation between particles at different locations, and which behaves as a power law as function of a distance between these two particles or positions, and this power law exponent is actually d minus 2 plus eta. We will talk about that exponent later. Again, we Fourier transform this correlation function or Green's function in momentum space, and this behaves as 1 over k to the power of 2 minus eta. And eta is called the anomalous dimensions. So you can see from here that we have many power laws, alpha, beta, gamma, and nu, and eta. This is the heart of this phenomena, the critical phenomena, that when there is a classical phase transition, and near that transition, all these physical observables shows a power law behaviors in terms of the small field or a small distance relative to the critical temperature. And that exponents define universality class of this phase transition. And many different materials or systems at the transition, and they may have exactly the same alpha, beta, gamma, nu, or eta. If they behave the same in terms of this critical exponents, then we could call them belonging to the same universality class. And if not, and they are not belonging to the same universality class. Okay, so that's probably the easier introduction to this critical phenomena in terms of the scaling phenomena. Then we come to this chapter 7. We introduce again a very powerful method called renormalization group analysis, or RG, which introduced by Kadanoff in 1966. So it's a very useful tool for us to probe this critical phenomena near the transition. We start from this high temperature and we cool down the system and until it reaches the ground state, or we start from the small cluster of the spins and we imagine that we enlarge the spin by putting more spins and more sites, and we enlarge the system, and we could use a bigger cluster or interactions among these clusters to actually get this couplings flows as a functions of system size or temperature energy. So we will introduce the basic idea of the RG transformations by introducing the so-called block spin, and we try to group a little cluster together of a spin system on the lattice, and then we try to sum over, do the partial sum in the partition function, and to get the interactions among these block spins. We may have this kind of this cartoon picture. So again, we will describe in more details later. We can monitor how this coupling flows under RG transformations. For example, this is J1 and this is J2. So J1 describes the spin-spin interactions between these adjacent sites of the spins, and J2 is actually this cluster-cluster coupling constant used this idea of the block spins to describe the system. So there's a relation between J1 and J2, and we could imagine that we could keep going to block more spins and more spins, and then we get to the thermodynamic limit. We can monitor how these couplings in the spin systems changes as you change the size of the block spins. And this actually leads to this so-called critical fixed points when the system reaches this critical point, and these couplings will actually flows to a fixed point that will not change anymore. And that could define the phase or the phase transitions. So that could actually distinguish one phase from another. And by doing these RG transformations, we could actually get to different regions of the phase diagram. For example, if we could find that this phase in the paramagnetic side is actually the phase where this J flows to J1 star, and this Ising case where all the spins are parallel corresponds to the phase where Ising coupling J flows to this J star 2. So different fixed points values of these couplings tells you that the system is in what kind of phases. So this is a really powerful method to study this phase transitions. And from this fixed point analysis, we could furthermore understand the origin of the scalings, because we could derive so-called renormalization group equations or scaling equations. And that scaling equations precisely gives rise to the power law dependence of these observables close to the phase transition. So renormalization group analysis is in fact a very rigorous and powerful method allowing us to study these critical exponents and the divergence of these observables near the phase transitions. And we will study near the phase transitions, certain variables are relevant and certain variables are irrelevant. For example, if certain variables flows to infinity under RG transformations, then we call this relevant variables. If this fixed point value under RG flows to 0, and it is an irrelevant variable. And the relevant variables tells us that this is relevant because it is the most important quantity near the transition, because it flows to a large value. Of course, any physical variables cannot be infinity, but this simply tells you that if you keep doing this RG transformation, these variables will become the most important variables of all, which tells you that you can ignore all the other variables in your system and simply just replace it by the single variable near the transition. So that's what we call the relevant variables. And likewise, if the variable is actually flowing to 0 or almost vanishingly small, which tells us that it is irrelevant, we could simply just forget about these parameters from our consideration. So it doesn't matter as far as this critical phenomenon is concerned, even though it exists in our Hamiltonian, but near the transition, it is irrelevant. So whether the variables are relevant or irrelevant is very important when we talk about this critical behavior. So then we will come to the actual calculations, and we will apply this RG for a two-dimensional Ising model, and we could calculate this correlation functions for this 2D Ising model. Again, there's a finite size effect, and we should discuss this finite size effect and some numerical simulations issues. So almost concludes this chapter, except now we should consider another example, which is the 2D XY model. That's chapter 8, say phase transitions of 2D XY model, which describes this transition between a superconductor and also a superfluid. And this is called costless solid transition. Okay, so this is a really important, famous example of the classical phase transition in a two-dimensional superfluid, and at finite temperatures there's a vortex binding non-binding transition, and that follows famous costless solids type of transition, and we will talk about that a later part of this course. And finally, we will talk about this critical phenomena near 4 dimensions, meaning when D is actually 4 but slightly away from 4 dimensions, say 4 minus eta dimensions, and many systems will behave effectively like this, where the dimensionality is somewhere between say 3 and 4 or 2 and 3 and so on. And we should apply this RG for this kind of a system near these 4 dimensions, and we derive these RG scaling equations, and we analyze these fixed points, and we could get 2 types of fixed points. One is called Gaussian fixed points. Another is called the Wilson-Fisher fixed point. And we will classify these fixed points when we get there. Finally, we will talk about this quantum phase transitions, which is a phase transition driven by quantum fluctuations and happens at 0 temperature. But the principles and phenomena of a quantum phase transition and quantum critical phenomena is really very closely related to these classical phase transitions that we describe over there, except that now the quantum mechanics will play a role. Instead of the thermal fluctuations, and we describe these quantum fluctuations near the GC, and we describe this critical region near the GC at the finite temperature. It's called the quantum critical region. So this is sort of a roadmap to outline the topics that we will describe in this course. So we continue. We start from this first chapter and first section of this course, which is Introduction to the Scaling Phenomena, or the power law behaviors of physical quantities. There are many power law relations in physics. This critical phenomena belongs to one subset of this general scaling relations or scaling phenomena in physics. But before introducing this scaling in phase transitions, we should introduce this more fundamental or more basic relations in physics, which describes some certain power law relations of the physical quantities as a function of, say, distance, the height or field, and so on. And we could even use a dimensional analysis, simply just analyze scaling dimension of physical quantities, and we know this power law relations of those physical observables. So, for example, if there are two measurable quantities that are related in power laws, and we call them exhibit showing this scaling behavior. So, for example, this Kepler's law in elementary classical mechanics, saying that this period of this planetary motion, say the Earth orbiting around the Sun, was a period t which is proportional to this radius or distance to the power of 3/2. Okay, so that is just famous example of this power law. And this non-trivial power 3/2 comes naturally from this Newtonian mechanics or Kepler's theory. And the second example is the phase speed of the shallow water wave. Imagine that there's shallow water with a height h, and this water waves shows some wavelength lambda. There's a gravity g pointing downwards, and we could calculate the phase speed, which we call the c, in relation to this g and h, which is c squared is going to be g times h, and or c is proportional to the square root of h, and that relation holds if h is much smaller than the wavelength. Okay, so this is well known. And again, so there's a power law which is square root of h for this phase velocity c in relation to this height. This is the second example of this power law relations of certain quantity in relation to some parameters which could be measured. For example, this height. But this is simply just limiting behaviors when this height is much smaller than this wavelength here. In general, this problem can be solved more precisely, which has this form, which I don't have time to talk about the steps towards that result, but only say that this is the general solutions if you follow this classical mechanics to calculate the phase speed of the shallow water wave, and you will find that the phase speed c squared is given by this hyperbolic tangent function, and when h is much smaller than lambda, it means that the hyperbolic tangent becomes about 1 over 1, and you get almost same behaviors, because now you could Taylor expand this hyperbolic tangent when this h over lambda is actually small. But this is a more precise calculation. But the question is, when we get to the same scaling relations or power law behaviors, just by doing this dimensional analysis, meaning can we get the same square root behavior by counting the scaling dimensions or dimensional analysis? In other words, can we just simply count the dimensions of all these physical variables, the phase speed and the density and its gravity, gravitational constant g, and so on? So if we do so, and so let me just write down this scaling dimensions of various parameters, say speed, the phase speed, which is length scale times 10, now this time inverse, and this density has a scaling dimension of this mass divided by the volume length scale to the power of -3, and this height as a scaling dimension of the length scale, which is the same as lambda, and this gravitational constant g as this unit of acceleration, which is length scale divided by time square. Again, h over lambda is almost 0. So this is simply just dimension analysis, and we could get to the same power law relations, and as we can see in just a moment. Okay, so I don't know the answer, but I can simply just guess that the c from the scaling dimensions has a relation to g and h by this following function. So c is actually has this square root of gh as a correct dimension multiplied by some unknown function, which I call this f function, which is a function of h over lambda. So I don't know what this f function is, but what I do know is that since h has a dimension L, which is a length scale, the same length scale for lambda, so this h over lambda has a dimensionless. So in other words, when h over lambda almost 0, and this function will becomes almost f of 0. Suppose that this f function is a well-behaved function in the limit of h over lambda approaching to 0, then we could safely say that this is the correct relation, because now the c is actually really proportional to square root of gh times a constant. But again, this is a bit dangerous because we don't know what this f function is. The only thing that we do know is that we assume this f function is a well-behaved function in that limit. But this is a big if. This is a big assumption. And many f functions in this critical phenomena that we will be talking about violate this kind of a hypothesis or postulation or assumptions that the f functions in many cases are not that simple. But here it looks like if f function is a well-behaved function and without singularities and divergence, and we get this relation, so even without solving the problem. So this tells us that this dimensional analysis may be useful to actually get the scaling relations of physical quantities other than critical phenomena. There's a second way of getting these relations, because there's no unique way to actually think of this c as this kind of combinations, the square root of g times h times the f function. The c could be equally well represented by the square root of g times lambda, because lambda has the same scaling dimension as h, which is L. As a result, c could be a function of the square root of g times lambda times another function, which we call this f tilde, h over lambda. And f tilde is a different function from the f function. But again, now we should be careful, because now we cannot say that when h over lambda is small and this f tilde function is a constant. No, if we say so, then this will not be the desirable result, because we need c to be proportional to square root of h, but not square root of g times lambda. So lambda has to disappear, and this requires some intuition. The physical intuition tells us that when lambda is large, then c is independent of lambda. In other words, when h over lambda vanishes, then this whole thing would not be a function of lambda. In other words, lambda has to be cancelled between the square root and this f tilde function. The only way that this could be achieved is the following. Cancel the lambda dependent. There is only one way to do so, which means that this f tilde function as function of x should behave as square root of x times another function, which we call this f double prime as function of x. So if I do so, then the c is actually square root of g lambda times f tilde, but f tilde now is kind of a square root of h x, where this x is actually h over lambda times this f double prime as function of h over lambda. So now you can see that this lambda actually get cancelled, and you get precisely the square root of g times h times this f double prime as function of h over lambda. But when h over lambda is very small, and you could safely assume that this is just a constant. And you get back to this correct power law behavior that c is actually proportional to the square root of h. So you see, there are two ways to achieve this goal, that C is proportional to the square root of the h. On the one hand, you could assume that this is proportional to g h square root times this f function. And number two is that this is equally well presented as the square root of the g times lambda, but this f tilde function is a non-trivial function of lambda because the lambda has to disappear by these cancellations. And again, we should assume that f double prime is a well-behaved function, and this should become a constant when this x approaches 0. Okay, so now you can see that even to get to this power law relations like this is highly non-trivial by dimensional analysis because we need to assume f function or f tilde function or f double prime function, which is not easy because the dimensional analysis cannot tell us anything about this f or f tilde, the behavior of the f tilde function or the f function or this f double prime function. So simply by dimensional analysis is not enough. So we need to know the physics or some educated guess or some intuitions, good intuitions from the physics point of view that these functions behave. But until then, we can only guess or assume. So we must know something about this f of f tilde or f double prime and so on. And this f tilde and f double prime are called the scaling function. And in this critical phenomena, this is the key because oftentimes if we are close to the transition and the physical quantities shows a scaling behavior as a function of certain variables, some power law multiplied by scaling function f or f tilde or f double prime, and how this f functions or scaling function behave in certain limits of this argument is the heart of our problem. In other words, we need to really find out and calculate the scaling function close to phase transition. Before the end of our first lecture today, I would like to make remarks. So remember this phase speed c is actually square root of h, right? So the h to the power of 1/2, and the Kepler's law period of this orbiting is about distance or radius to the power of 3/2. So these power law exponents, 1/2 or 3/2, are rational values. But there are other scaling behaviors or power law behaviors close to phase transitions that we will be talking about later. They have irrational exponents, say alpha, beta, gamma, and delta, and so on. They could be irrational number. Of course, they could be rational as well, but in many cases, when the system are very close to phase transitions, all these critical exponents, alpha, beta, gamma, delta, and so on, they all are irrational exponents. There's almost no way by using dimensional analysis, because from the dimensional analysis, all these powers are all rational ratios between rational numbers, right? So this is some multiplication or divisions of integers. So they are all rational values. As a result, from this dimensional analysis, you can only get this rational power law. But this is different from this critical phenomena because close to the critical point, all these exponents are irrational numbers. So we cannot simply just use dimensional analysis to simply just derive such a power law behavior with the irrational exponents. So that's not possible. So this is the end of our first lecture. Next time, we will start to introduce a real physical system which shows this phase transition at finite temperature. So we will introduce this liquid-gas transition and also the magnetic spin system or magnetic transitions. And we will compare these two levels of phenomenology, and we will see that even though these two systems are very different, one is from this, say, liquid-gas classical, another is from the spin, but close to this finite temperature transition, they behave exactly the same in the sense that all these critical exponents are exactly the same. So that's something, I think, unexpected or surprising to many physicists over decades. And still now, we discover seemingly unrelated physical systems which belong to the same universality class. So what is the principle guiding universality class, and this giving rise to such fascinating critical exponents and the power law and scaling behaviors will be the topic of our course. So I hope everyone enjoyed this lecture, and because this combines experimental observations and statistical mechanics, and also the principle of a phase transition, and so that you could understand this seemingly unrelated phenomena in a coherent way, so that you understand, oh, this is a consequence of a universality class, a scaling relations, and so on. And in physics, many branches of physics, there are many examples of such kind that system undergoes a transition from one phase to another phase. And to describe correctly how this phase transition occurred is our focus. And hope that by the end of the semester, you will appreciate this phenomenology and also this powerful theoretical tools that allows us to understand such a complicated and yet surprising phenomena. That's the end of our first lecture, so I'll see you next time.